element there is an inverse, and this means that if we set the Rubik's Cube on fire, we cannot go back to the original Rubik's Cube. So this is like a toy example our physical system could, which enjoys this symmetry could behave. So we will not set things on fire, but there are already non-physics. Yeah.
Do these symmetry operators then have the structure for semi-group if the only thing missing is an inverse?
You can they have structure of categories if you want. This is the right mathematical framework. Fusion categories, because these operators they fuse in different codimension, and some they could also have a structure of groupoids.
Yes.
Okay, this is as far as I can tell you, but yeah. Okay. I will not spend much more on the mathematical side of this, but there is a very interesting mathematical side of these aspects for sure. As I told you, also physically, I will not set things on fire. I will just talk about systems that we know very well already. But before going to that, let me just briefly summarize this generalization, what we know about this generalization. So we can have concept currents, which are one form of vectors, and this will generalize to P plus one form currents for a P form symmetry. We can define a charge, which is the same, just that now we integrate in a lower dimensional space, which is sigma d minus P minus 1. This charge, of course, is conserved, and the conservation comes from the continuity equation, from the conservation of the current. We can define a symmetry operator by exponentiating, and we have already understood that these operator, they fuse or they composition rule are according to group laws. So this is valid for both zero form and P form symmetry. We can extend this. We can allow for more general fusion rules of composition, like non-invertible composition, as I told you. So in 2 dimensions, these n are numbers. In higher dimension, these n are also numbers, integers, but they can be seen as partition functions of topological quantum field theory. So in higher dimension, this n is usually written as a partition function of a topological quantum field theory. Okay, and whereas in 2 dimensions is already a number, so that's are already integer numbers. That's the key difference between 2 dimension and higher dimension. Then we have generalized. Well, the charge, the symmetry operator act on charged operators of the quantum field theory. Otherwise, we won't have the symmetry. So they need to act non-trivially on something of the theory, or some operators, and they act via linking in this way. So we have the standard linking of a point like charged operator, and we can also have a linking of extended operator, like for example Wilson lines and so on. So this is an action by linking, and the action gives the exponential, the group element. So not everything is good for discrete and finite symmetry, but only a certain aspect. We can define, of course, we cannot define a current, but we can still define topological symmetry operators. So the charge and the U are topological operators. For the continuous symmetry, this is easy to show just from the continuity equation, but for the discrete symmetries, we already start with a topological operator. Very importantly, what we can do is we can study how the system reacts via coupling the system to a background for this symmetry. For continuous symmetry, zero-point symmetry, the standard way is acting, the minimal way is acting is coupling a mu, a gauge field for the symmetry, which is not, we don't do path integral over A, but we just couple the theory via this coupling with the current. And similarly for P-form symmetry. And for discrete symmetry, we can do this as well. We can couple the theory to discrete backgrounds, so to holonomies which are non-trivial in Zn, for example, like this. And this is valid for both zero for symmetry background, which is a one form of this type, and P for symmetry background, discrete, of course, which are P plus one form of this type. So this is how we couple two background fields, and this is very important because it's basically the key of this talk, and is the meat of this talk. In particular, we want to study an anomalies, for example, of quantum field theory, and to study anomalies of quantum field theory, we have to couple the theory to background fields. Okay, so this is the theory behind these generalized symmetries. Of course, it was a very brief summary, but let me show you an example. An example is the 1 + 1 dimensionalizing CFT. So if we tune the Ising model to the conformal point, we have a CFT, a continuum model, which is a CFT, and is described by local operators, which is the identity, the spin, which is sigma, and the energy, which is epsilon. This has three topological lines, this theory: the trivial line, the generation of a Z2 symmetry, which exchange the direction of the spin, and also a duality interface, which is called the Kramer-Vanier duality line. Basically, this acts on sigma like this, and the duality line acts on the energy operator by sending the energy minus the energy, so it's like a D2 symmetry, but it acts on sigma in a very particular way, which I will tell you in a moment. But let me also tell you how this line, the composition rule of this line. So if we take n composite with eta composite with eta, we get 1. So this is a Z2 line. You get eta composite with D, and D composite with eta, we get this relation. And also D composite with D, we get this relation, which is 1 plus eta, and this is basically the fact that D is a non-invertible interface for now. There is a duality, which means that the Ising model and the Ising model quotiented by the Z2 symmetry, which is generated by eta, are dual to each other. And at the critical point, the CFT is self-dual. So these two theories are basically the same at the critical point. So this means that at the critical point, the D Kramer-Vanier duality line is basically asymmetry of the theory. So this is because it's a self-duality at that critical point, and the topological line generates a non-invertible symmetry. And how yeah.
So I guess when eta fused with D, it should equals D, right? Instead of
sorry, there is a typo. Yeah.
Okay, sure.
There's a typo, is D. I agree. I apologize about that. Okay. How it acts on a sigma spin? Well, it sends this order transition. Basically, from if we exchange the position of sigma with the duality line, which is D, the blue line, then it sends the sigma on the mu operator, which is the disorder operator. So this is an operator of the T mod Z2 theory, and is attached to a eta line. This green one is an eta line. So this is basically generates a twisted Hilbert space for this theory, if you want. Or if you want, it's a defect attached to a local operator, which is mu. And this local operator will appear only at the end of the defect. Okay, so this is a particular feature of non-invertible symmetry that acts in this way on some operators of the theory, and it will appear also.
Excuse me.
Yeah.
Are there any operator that charged under these non-invertible symmetries? And
yeah, this is the way sigma is charged under non-invertible symmetry.
So it's not a
also, I think
compared to the previous.
Yeah, and epsilon is also charged. It sends epsilon to minus epsilon, if I remember correctly.
Okay, thank you.
Now I'm going by memory, but it should send the energy to minus the energy also. So everything is charged apart from the identity. Okay. Generalization to higher dimensions. There are many generalizations to higher dimensions. In particular, there are generalization of the Kramer-Vanier duality to 4D n equals 4 super means. But let me tell you about another generalization, which teach us that these non-invertible symmetry are ubiquitous in quantum field theory. So if we have an ABJ anomaly, for example, in QED, we have an ABJ anomaly for a U1 axial symmetry. We thought that this symmetry was broken quantum mechanically. So quantum mechanically, this symmetry was not there because of the ABJ anomaly. And the Beaton anomaly means that these F are basically field strength for dynamical fields. So this is not a top anomaly where this would be background, but in this case, A is a dynamical field, and so this tells us that there is something weird going on in the theory at the quantum level. So we can try to construct a concept topological operator out of this, of course. We can. This is basically a total derivative of our Chern-Simons form, and we can send the D on the other side, and we construct a new current. A new current is called the page charge. I will not show you this page charge, but the page charge in general is not gauge invariant for any value of the symmetry transformation. However, we can see that for the fractional value of the symmetry transformation parameter, we can define a topological operator. This topological operator contains the, see here I didn't write, but it contains the odge of the current JA. And it contains also a Chern-Simons term of this type, where A lives only, little a lives only on the defect, and it couples to big A, which is the bulk A, the bulk meaning the theory A, in this way. So A, big A is the field, gauge field for the bulk for dimensional theory, and little a lives only in the defect. Then upon integrating out the little a, what you get back the page charge. So that's why how this is related to the page charge. However, this is a gauge invariant, and topological operator. So now we have a true and honest topological operator of the quantum field theory. We had to add this gauge field on the defect, but at the cost of having this operator non-invertible, because if we try to compute the fusion of this operator or the composition rule of this operator, we see that this is not equal to the identity. With the inverse, of course, or with the putative inverse, this will not be equal to the identity. And let me tell you that this happens every time there is an anomaly of the ABC type. So we have three background fields, A, B, and C, involving this anomaly, and we gauge two of them. So if we gauge two of them, then we can construct a similar operator, which basically we can construct a topological operator in a similar way. So that's every time we have an ABC anomaly and we gauge two of these two symmetries, like AB, AC, or BC. So that happens very frequently. Okay, there are some applications of these non-invertible symmetries. I won't discuss them, but in order to motivate this, this is very interesting because we can, for example, compute the coupling of the pi zero with the electromagnetic field in the pion Lagrangian. We can compute also by using some symmetry, then some hypothesis about the non-existence of symmetry in quantum gravity, or that the symmetry must be at most approximate at low energy theory of quantum gravity. We can constrain and for example, the neutrino mass to be small. We can try to address the strong CP problem with no other particle additions. And there are many, so there are applications to axion cosmology. And this is a very vibrant field at the moment. And people are trying to also apply this to phenomenology other than, condensed matter, which is basically the standard, the more natural it's in the eyes of the beholder, but, it's a natural application, I would say. Good. So any question about this generalization of symmetries? Good. So let me proceed. Now, how do we capture the structure of this symmetry? Well, a very nice way to capture the structure of this symmetry is to use symmetry topological field theories. Symmetry topological field theories are an organizing tool for finite symmetries. So from P group, P for symmetry, non-invertible symmetry, all of them. They usually involve a BF theory or a discrete gauge theory. One can study generalized higher charge of a quantum, a generalized higher symmetry charge. So these are all buzzwords that I'm telling you now without explaining, but I will explain some of these aspects, of course. You can compute action on charge operator from the symmetry TFT. You can compute anomaly. You can study condensation defect, which is its own area of research, basically. But you can study many things about symmetry. In particular, I would say for finite symmetry, this is you can study all the full structure of the symmetry. So that's why the Symmetry TFT are very natural. And also, if you try to construct to study this in generalized symmetry in terms of category, the bulk direction is pretty natural. In order to understand how the category is the structure of the full category. So this is also mathematically, mathematically it also emerges this extra direction. So that's why Symmetry TFT are very useful. Good. So what is a Symmetry TFT? So the ingredients of a Symmetry TFT is a physical theory with a symmetry S. So a theory we call T and a symmetry is S. And the goal of the Symmetry TFT business is to separate any aspect of the symmetry sector from the physical, well, not the physics, but the physical quantum field theory T. To do so, we define a D plus one dimensional topological field theory, which has two boundaries. One is a symmetry gap topological boundary, we call B symmetry. It's basically a gap topological boundary of the topological field theory in the bulk, so this yellow boundary. And one is a physical boundary, which we call a B physics. It doesn't have to be gapped, of course, because we want to study also theories that are not topological. And the procedure is now to do interval compactification. Since this is a topological theory, we are not afraid of doing that because the theory doesn't change under shrinking the interval. And if we do that, what we get is a theory with a symmetry S. And if we change the symmetry boundary, we also have different theory after doing the interval compactification. So we'll show you an example in a second. Before showing you the example, let me tell you that you can also study the operators. So a topological operator that implements a global symmetry of the theory T are basically topological operator of the bulk theory, which I call Q. So this could be a P plus one operator, QP plus one. So this means that the dimension of the operator is a P plus one dimensional operator. And we can project the operator on the symmetry boundary. If we project the operator on the symmetry boundary, we get basically a symmetry operator once we do the interval compactification. If we instead take the operator to lie along the interval direction, we source a physical operator at the physical boundary. And this is only allowed once we impose the Dirichlet boundary condition for certain gauge field in the bulk. And if you do the interval compactification, you get a charged operator. And moreover, you can also compute the action of the symmetry operator on the charge operator by linking in the sense that you can link a topological operator in the which is D minus Q minus one dimensional in the bulk. You can project on the boundary. This will still link this line. And if you project onto if you do the interval compactification, you get basically the linking action of the charged operator of the theory on the charged operator of the theories. This is the local operator in this case, because it is bidimensionality, but it can be Q-dimensional. Okay, so this is how the operator look like in a Symmetry TFT, and now they are related to operator of the boundary theory. So maybe to clarify, let me show you an example. There is a original Symmetry TFT, I call it original Symmetry TFT, which is the Symmetry TFT for 1-4 symmetry. This was derived from holography by just looking at topological sector to be supergravity. So you can treat this BF theory of 2-4 fields on a space M5, which is now not ADS, but it's this space with two boundaries. So now we forget about the origin of this, and we take this theory to describe only the symmetry, the 1-4 symmetry sector. So this describes two discrete ZN gauge fields. If we exponentiate these two operators, this will create the topological operator of the theory. Now we can choose which topological operator extend goes from one boundary to the other, and which topological operator links with this operator extended in the interval direction.
Sorry, it's a really dumb question, but
Yeah.
does the spectrum of gauge invariant operators of n equal to 4 organize under this symmetry in some interesting way?
The spectrum of line operator organized under this symmetry. So
I see. The spectrum line operator. Okay. And in the ATS dual string, what would that correspond to?
Right. So now I'm telling you. So this is if we take, for example, the F1, if we take a Dirichlet boundary condition for B2, so a fixed B2 at the B symmetry, this means that we can take an F1 to go from one boundary to the other. And this F1 will generate a line operator in the symmetry in the physical boundary, and this is the Wilson line. What charges the Wilson line is the holonomy of C2, which we interpret as in a particular topological limit as the D1 string. And this the action of this is by linking. And of course, you can choose another boundary condition, and this is for SUN gauge group, and you can choose another boundary condition where now this is reversed, and this is B2 freely varying C2 fixed, and this tells that the theory here is PSUN rather than SUN. So this is how it works, and this is very general in Symmetry TFT.
May I have a question?
Yeah.
So what is the boundary in this setup? So is it constructed in type 2B? Like end of the world?
Now we take this action, we truncate to the topological sector, and we forgot about completely the origin of ADS. I will tell you how you can try to link this with the boundary of ADS in a second. This is not.
So you're thinking about like some what is I mean in the type 2B setup. So I'd like to see what it is.
Yeah, so if you want to do holography, there is only one boundary, right, in ADS.
So it's a boundary in a space-time?
It's a boundary. This is M5, it's basically space-time. M5 is the M4, the boundary M4 is where the physical theory lives, if you want. And this is where the symmetry.
I see. Okay, I see. Yeah, thank you.
This is related to the previous picture that I showed to this. It's not related to holography yet, even though it comes from holography. And now we'll try to link the two pictures.
Yeah, I see.
But this is only an attempt to link the two pictures. It's not yet super satisfying. But there is a clear connection from how to derive this symmetry TFT from string theory to there is a clear connection to the action, and then the problem is which space you use. If you use holography, then you have only one boundary. So you basically imposed the yellow and blue boundary, so the physical and symmetry boundary, basically on top of each other. That's what you can do in holography. But this is if you want a way of trying to separate the symmetry sector from the rest of the theory, and it turns out to be useful. Let me also say that in holography, this direction is not the physical direction. Of course, you can try to relate this with the bulk direction, but it's yet a bit. There is some work to be done there to show this. Anyway, I will try to get back to this in a couple of slides. So ask me again if you have a conclusion. But these were just the two boundaries of the Symmetry TFT, one the physical and one where the physical theory lives, like n equals 4 square mills, and this is the symmetry boundary. And when they are separated, it doesn't have any global structure specified. And when we do interval compactification, the global structure gets specified. That's the main feature of Symmetry TFT. Or this symmetry TFT. Okay, good. The main idea that we have is that there is a rich interplay between two research areas, one which was very fashioned in the 90s, which is quantum field theory from string and theory and holography. Well, was fashioned in the 90s, but up until recently, I would say, and now which is very vibrant now, which are generalized global symmetry of quantum field theory. And there is a very, very nice connection. And the program is to connect is to see the UV origin of the symmetry topological field theory, and in particular the UV origin of the topological operators in the symmetry TFT as branes. So the branes encode the topological operators of the symmetry TFT, at least if you have this stringy origin in mind. Okay, so let me tell you a bit about the motivation of this. Of course, we want to study theories that don't necessarily have a Lagrangian description, from holography, from brain engineering. And this theory they can be 5, 6D, class S, in 4D. We have many examples of this theory. Generically, they don't have they do also have interesting symmetry sectors. And moreover, branes and geometry give us an alternative physical way of understanding properties of global symmetries that are categorical, as we will see. And moreover, as I already told you, categorical symmetries are encoded by Symmetry TFT, and in particular are encoded by all the information of topological operators of the Symmetry TFT. Okay, so now after half of my talk, I'm finally to the outline. So I probably won't have time to discuss about all these 3 points, but at least 1, 2, or 3, which are Symmetry TFT from string theory, probe branes and symmetries, and some example of Symmetry TFT from branes. And then if I have time, a couple of minutes, I will skim some result about non-finite symmetries. So Symmetry TFT from string theory. So this is how it was basically born. So we study some string and theory on a compact singular geometry, which we call xn+1, with a boundary or link, which we call Ln. So this is a conical geometry. It has a singularity at the tip of the cone, and it has a boundary, which is Ln. Now we associate this picture, at least in a limit where we in a topological limit, if we truncate this to the topological sector, we can forget about once we truncate it to the topological sector. What we do is that we are focusing basically on flat gauge potential in D+1 dimension. So we're focusing on a theory which describes a flat gauge field in the bubble. And with this means that we are basically either implementing a higher derivative expansion. So we are taking just the first derivative term, which can be, which are usually, in this case are the topological term, and we forget about 2 derivative terms like kinetic terms and so on and so forth. But there is a better justification for this, is that we are, which was given originally by Witten, once we truncate to the topological sector of the 10 or the 11 dimensional supergravity on this space, we basically are describing the theory of flat gauge field. And since we are interested in finite symmetries, well, we are only interested in flat configuration for this gauge field. And this means that we can forget the non-flat configuration. So we can forget the kinetic term, which describes only the fluctuation of the non-flat part, and also other couplings to the gravitational field and so on and so forth. And so once we have truncated to that sector, we are free to choose our space, because now having truncated away all the effect to the gravitational, to coupling to gravitational background, we can basically choose our space as we want, because we are in a topological theory. And so the topological theory doesn't depend basically on the space where you put the theory. So it doesn't depend on the metric in particular. So that's a bit the procedure in geometric engineering. And in particular, if you do this procedure, then you can associate the infinite boundary, the boundary at infinity, with the symmetry boundary, and the tip with the physical theory. So that's a way of identifying these 2 boundaries. And in holography, this is a bit less clear, but there is a sort of analogous picture now. So you have a background, which can be ADS, which is xn+1. It has a boundary, ADS. And then the physical boundary is not associated to the tip of the cone, but is rather smeared in the bulk. And whereas the symmetry boundary is the boundary at infinity. So this is because the theory in the bulk is dual, or correspond to the physical theory. So it's a bit less clear, but this picture I think it's the closest one to associating these to the Symmetry TFT geometry. So in a way, there is a sort of relation between the bulk direction in holography or string engineering and the interval direction of the Symmetry TFT. Of course, in holography, you cannot do interval compactification because it will change drastically the bulk theory. But once you truncate to the topological sector, you forget about the original interpretation of the direction in terms of the holographic direction and just treat this direction as the Symmetry TFT direction. Okay, so this is a way of relating the two pictures, holography picture with the Symmetry TFT and the string geometric engineering with the Symmetry TFT. Okay, so branes and symmetry. Again, a first encounter of this brane and symmetry are strings in a DS file cross S file. As I told you, we truncated the theory, the full holographic theory, to the topological sector, so the BF theory that we've seen before. And in particular, the Symmetry TFT does not really need the Lagrangian, it's like QFT, right? We don't really need the Lagrangian. What we really need are all the operator spectrum, like the topological operator in this case, and the correlators between these operators. So how the operator charge is charged under each other. And so a very useful way to see this is to start from the Lagrangian, the BF Lagrangian, and couple the BF Lagrangian to brane sources. These are localized brane sources for F1 and D1 strings. They couple with the B2 and C2 in this way. And if we study the equation of motion or the Gauss law, we have this equation of motion. We plug back into the action, and plugging this back into the action is basically computing the expectation value, or the exponential of the expectation value of two topological operators that are linking in a standard of linking way. So they're linking in 3 dimensions, the two circles will link. In this case, in 5 dimensions, two surfaces will link. So this is the standard of linking. And so the evaluating this action on this equation of motion is basically computing this expectation value. It's the same computation. And what you get is that if you exchange link with unlink, then you get basically the right expression for how the two operators are charged under each other. So this means that we can use the Lagrangian to understand this theory, but also use branes and how they link. So all the information about this theory are encoded in this linking, in these two topological operators and their linking. That's all there is. And of course, there is of course more complicated structure, but this complicated structure can be constructed from this. Okay, so then now the goal is to try to generalize this to any sort of background that we know, either from string theory, from holography, or from geometric engineering, or from brane engineering. So what we want to focus on is the flux sector of supergravity in 10 or 11 dimensions. And the flux sector of supergravity, like either a equation of motion or a Bianchi identity, can be recast in terms of a D plus 2-dimensional action, where big D is 10 or 11. So this is an auxiliary action, such that if you do variation with respect to F, what you get is the equation of motion or Bianchi identity of the flux. So you can try to do this exercise for type 2B, and then what you get is the type 2B Bianchi identity or equation of motion, where now we use it. We treat these as all as Bianchi identities using the fact that using this Hodge duality. So just by doing variation calculus with respect to F of this action, you get the Bianchi identity. So that's a tool, but it's a useful tool because now instead of dimensional reducing the Bianchi identity, you can dimensional reduce this action directly on the link. So compactifying this action on Ln to get the Symmetry TFT. So how we do this? So we start from 10 or 11 dimension, from the +2. So this is the action that I showed you in the previous slide. We reduce on Ln, and we find a topological action in D+2 dimension. So let me tell you what the dimensions are. D is 10 or 11. N, little n is the dimension of the link, the space where we reduce the theory on. The physical theory lives in D dimension. So this is the physical quantum field theory that we engineer with our background. The symmetry TFT lives in D+1 dimension, and the auxiliary topological action that we relate to the symmetry TFT by descendant basically is in D+2, little D+2. Okay, so this is a bit how the dimension work. And we implement expansion. There is the following ansatz where we expand around the non-trivial cycle of the compactification geometry. So this is the volume form for the Ln. We expand both the field and the sources. So the Bianchi identity that I showed you before are in general Bianchi identity with the probe brane sources. Okay, so the resulting auxiliary action, topological action that we get from reducing these is generically looks like this. So we have a polynomial in terms of this little fi, and a coupling of fi with the brane sources. And we can see that this action on MD+2, once we integrate on a space with boundary, so in a space on MD+2 with a D+1 dimensional boundary, we get the symmetry TFT. So the space has a single boundary. It doesn't have a non-trivial topology because this is really just an auxiliary dimension, the +2 dimension of this theory. And the physics is just contained on this MD+1, on the symmetry TFT. So this is just an auxiliary way in order to have no issues with gauge invariance and so on and so forth. And it's very democratic. So this will allow us to treat all the fluxes democratically. Good. So, okay, an example, we can have this kind of term, A alpha, which is usually an integer number, F wedge F tilde. So this is a result of this D+2 dimensional action, and F are coupled to J, to the sources in this way. And so these are the BF terms that are generated by two types of branes. And in particular, we can now solve this theory. So we can solve the equation of motion and substitute back F in the F in terms of J. And what we get is like the case of the BF theory for n equals 4 super n is we get the linking of two topological operators. So we get the correlation function between two topological operators. So this is what allow us to describe this BF theory just in terms of branes or topological operator. Good. So this BF term can be derived both from the Chern-Simons term if we have a background flux. So this is the case for the n equals 4 spay and means from ADS5 cross S5. We have a F5 flux on S5, and the Chern-Simons F of F5 of the 10-dimensional Chern-Simons gave us the BF theory. Or if we have torsional cycles, we can have BF term from the kinetic term directly. So this is because if you want this term F dF tilde will allow us to have an omega which is non-closed, and we can describe the torsional cycle in the continuum limit in this way, and where alpha is the this d omega wedge omega tilde, where these are the pairs, the little omega and big omega, and little omega tilde and big omega tilde for torsional cycles. So that's just to tell you that torsional cycles can give BF term from the kinetic term. Because basically the non-topological part is taken into the compactification space, and you still have a topological term in the external space where the symmetry TFT lives. So that's why this happens. Okay, then by solving this action, we can really relate. We can compute the linking of the two branes, and the linking of two branes will tell us about the two-point function of two topological operators that are linking or not linking. So that's and that is basically the building blocks of this symmetry theory. There is other couplings that can appear, other couplings that are comes from other type of linking, like these Borromean rings. I don't have time to describe how this linking works, but there can be linking among free branes, free type of branes in this way, and these usually give us coupling that will correspond to anomalies under choosing particular boundary conditions. So this is important because remember that at the beginning I told you that ABC anomaly were crucial to get non-invertible symmetries, and this is a way where you get ABC anomaly, where J correspond to the branes that generate the symmetries whose background are ABC.
Excuse me. So this
Yes.
three symmetry can be in general different forms, or
Different forms. Yeah, and
Okay,
here
thank
I'm completely general. I will show you an example now. Good examples. We know that SUN or PSUN super means are described by this Lagrangian. If we start from SUN, this has two symmetry, a Z2M0 form symmetry, which is a chiral symmetry that comes from the original symmetry, which is quantum mechanically broken to a Z2M, and then we have a 1-4 symmetry which acts on the Wilson fundamental Wilson line in this way with an exponential. So that's how the symmetry of SUM super M's are. And there is a mixed dot anomaly which is of ABC type, and now it's ABB because the anomaly has a constant factor which is 2 pi I over 2m, and it depends on the background for the 0-4 symmetry, which is A, and the background for the 1-4 symmetry, but quadratically. So this is a background for the 1-4 symmetry B2. B2 is the background for the 1-4 symmetry. And this is well known. This is one of the first example study that if you now gauge the B2 of SUN, so you want to go to PSUN, so gauging the 1-4 symmetry will take you from SUN to PSUN. Then if you gauge B2, this anomaly will tell that there is a non-invertible symmetry for the PSUN theory. In fact, you can construct a topological operator very similar to the one that I showed you before for the QAD case at the beginning. So the QAD case was a Chern-Simons theory A little a dA plus a coupling A with F. And now the change is that now the little a coupled with the B2 instead of the field strength of the bulk gauge field. So it's a very similar topological operator, but it couples to this B2. Okay, so how we can construct these symmetries in terms of branes? Well, we need to find a holographic dual. An holographic dual for n equals 1 super m means, not exactly n equals 1 super m means, but a holographic dual to a theory that shares symmetry properties with n equals 1 super m means is the conifold with MD5 brane on S2. So how this is related to the SUM super m means is basically they produce the same theory in the infrared, right? There is a chain of cyber duality energy flow of this theory, of this conical theory, which is this quiver. And this chain is connect the two RG flow, the infrared, the SUM going to the infrared, and this going to the infrared are connected in this way. So these two theories have these two symmetries. So they have the same symmetries, and they have the 0-4 symmetry and the 1-4 symmetry, and they have also the same anomaly. Good. So we can study the geometric background for the conical and try to see what are these topological defects. And indeed, we can implement the strategy that I told you before. We start from that the D plus 2 dimensional Lagrangian for the flux sector, which is where D is 10 or 11. In this case, is 10. We get a 4 plus 2 dimensional action of this type. So this is basically the BF term for the one for symmetry. And we also get a triple coupling of currents. So this will correspond to a source of to the brane generating the symmetry, but in terms of the Lagrangian, this corresponds to the ABB, to AB to B2 anomaly. So you can see this anomaly either in terms of topological operator linking in M D plus 2 or D plus 1, or you can see this theory in terms of Lagrangian just in terms of background fields. And this is the BF term. So the summing these two terms will give you the Symmetry TFT. There is also another BF term, but I want to show just the key aspects of this theory. So we can implement this strategy in order to find the Symmetry TFT. And but this gives us a direct link with the UV origin of this topological brane, of this topological defect. And the UV origin is given in terms of this brane. So the zero proximity defect are given by D5 brane wrapped on S3. They will span three-dimensional, free direction in the M4 space, where M4 is a slice of the five-dimensional bulk geometry. And these D5 branes wrap S3. Good. So we can study now the low energy action of these D5 branes. This contains the two following terms, the low energy action, a DBI term and a Wetz-Zumino term. In this case, the DBI part is not relevant in the topological limit because it contains only kinetic terms, and these we know that these don't describe the physics of flat gauge field. They only describe the physics of the non-flat part. So we only truncate to the topological sector, and the topological sector is described by the Wetz-Zumino term. So we take the Wetz-Zumino term of the brane. This is this following coupling. We have D little a. So this A1 is a one gauge field that lives on a D5 brane, and these are all the bulk Ramon fields. There is also a B field, so a minus B here, but which I omitted. But it's not super relevant here because you can integrate on S3. The integration on S3 will give from C6 you get a C3. So this is the way we expand C6 because the D5 brane wraps S3. There is an F3 which generates which sources a Chern-Simons term. So this will come from C2 DA, and if we integrate by part, we get a CF3 which gives M. So this is the D5 brane flux. And also there is a coupling with a little B1, which is the expansion of C4 on the volume on the S3 as well. Okay, so now we have this topological operator in the bulk, and we want to study how this topological operator behaves in the boundary. In order to study how this topological operator behaves in the boundary, now we want to, this A1 should be without the one. So this is a one form, but A1 lives only on the brane. Whereas B1 and C3 live in the bulk. So then we have to choose boundary condition for the field living in the bulk. And the boundary condition for the field living in the bulk, we take C3 to be dynamical at the boundary, so we take to freely vary at the boundary, and we focus on two choices for B1, which can be either fixed or freely varying, so either Dirichlet or non. So in this case, we get two scenarios. For B1 freely varying at the boundary, this theory trivializes, becomes basically a trivial theory, this one, the Chern-Simons plus this, because these are all dynamical, and you can see that this is, if you know this, this becomes a Z1 Dirac-Witten theory. So Z1 meaning the group Z1, which is trivial, and so becomes trivial. But if P1 instead is a background field, meaning that we fix the value of B1 at the boundary, then we basically generate the D3, the D topological defect, the one that generates the non-invertible symmetry, the non-invertible 0-4 symmetry for the PSUM theory. So we basically recover the behavior of the non-invertible symmetry for the N=1 PSUM theory from this background and from the branes. So this is the action of the brane in topological limits, so where we consider only the Wetz-Zumino term integrated on S3. Okay, so any question about this? Maybe, yeah, it was a bit quick, but if you have a question, please do ask about it. The strategy is just dimensional reduction, both to get the symmetry TFT, but also to get the Vor volume action of the brane, and also other structure of the brane properties. And another property of these defects is that we can, being non-invertible symmetries, they must have some non-invertible action on certain operators. So this action is what it's a specific feature of non-invertible symmetry. So this is a non-invertible action of charged operator. And there is a similar non-invertible action for Toft line, so that this D three-dimensional defect generated zero for symmetry in PS super Young Mills n equals 1, they will have a Toft action, an action on Toft line in this way, where now there is the operators on the right-hand side is not genuine anymore, but it has to be attached to a surface, with a surface given by the exponential of the B2 field. What this corresponds to, if you're familiar with brane systems, this is basically comes in terms of branes, this basically comes from an Ani-Witten transition. This is because the Toft line can be engineered by D3, extending on the radial direction and wrapping the S2. And the D3, sorry, this is a D3, not an N3. The D3 defect is basically, as I told you, a D5 brane in this way. And by dimensional analysis, you see that these two brane link in an Ani-Witten type. And so if you exchange their position, they must create an F1 in between. And so this F1 is basically, in the topological limit, it corresponds to the Vor volume, to the action of, to the integral of B2 on sigma. So if you dimensionally reduce this system and Ani-Witten transition, you get exactly this feature of the non-invertible symmetry. Okay, so let me just go a couple of minutes on this symmetry theory for non-finite symmetries very quickly. So this, of course, include continuous symmetries. And symmetries whose parameters, instead of being finite, are infinite, but are discrete. So these are non-finite symmetries. So they can be continuous or discrete symmetries, that are non-finite. An example that I showed you before, this non-invertible symmetry coming from a BG anomaly, is a Q mod Z symmetry, whose parameters are in Q mod Z. So it can be general fractional number for this parameter, P over N. I show you just the 1 over N, but this can be P over N in general. So the question that we ask is there a symmetry theory which captures the non-finite symmetries properties of a QFT? So the structure is to look at the boundary, at the bulk theory. Now that is not a topological theory, is rather a free theory, like a Maxwell theory, coupled to some Chern-Simons terms, which correspond to this ABC anomaly, or the ABJ anomaly in this case. And try to implement a procedure which allow us to factorize in a particular limit, in the limit where we shrink the interval to 0, the QFT part with the bulk part, so that we really focus on the symmetry property of the QFT part. So I don't have time to discuss this in details, but the way you get a proposal for this symmetry theory is the following complicated theory, which consists of many Maxwell fields of different degrees with two Chern-Simons couplings of this type. And upon choosing certain boundary condition of the field, so you have to choose boundary condition of this field. Now you have to study topological operator of this theory and boundary condition for these fields. And what you get are, if you choose A1 and B2 to be Neumann, to be Dirichlet, and C1 and C0 to be Neumann, you get exactly the Q mod Z 0 for symmetry at the boundary. And the topological operator that you get is basically this one, which corresponds exactly to the non-invertible 0 for symmetry for the axial Maxwell theory. So there is also a non-invertible 1 for symmetry that you can recover from this. But what I want to say is that from this action that you can derive from type 2B string theory on S2 times S3, you obtain the topological defect for the axiom Maxwell once you choose a specific boundary condition. And as a final comment, you can get topological dressing, so this part of this operator, from branes as well. So the UB origin of this topological dressing is given by Ward volume action of branes. Okay, so let me conclude by saying that branes and their linking properties provide not only the topological operators, but provide the full information about the symmetry TFT, and also the full information about the structure of the symmetry. So we saw how to get the bulk Lagrangian from various brane linking. And this is an alternative if you want to higher categories. If you want to understand how these higher categories work, brane, string theory, geometry, and branes are basically, give us a physical way of understanding these properties. Okay, so good. So the string theory, as I told you, and holography provide access to these properties. And we also have made a step forward into describing non-finite symmetries and to describe them in a mathematical way by introducing the symmetry theory for the non-finite symmetry. So the hope would be to really get a categorical definition of non-finite symmetry as well. And again, Ward volume theories of brane can exactly provide a topological dressing of the non-invertible defects. It would be nice to investigate this further to show this better. So this was just a very quick evidence that we get from certain argument that this brane will describe the topological dressing. And finally, it would also very nice to study the symmetry theory so the theory of symmetries for non-finite symmetry, and in particular for continuous symmetry, which are space-time symmetries. And with this, I thank you for the attention. Sorry for being a bit over time.
Thank you so much, Fabio. Are there other questions?
Could I ask again, what exactly is the non-finite symmetry? I didn't really get it.
Okay, non-finite symmetry could be a continuous U1 symmetry, zero form or P form. And what I'm claiming is that this in the bulk can be described by Maxwell theory, Maxwell gauge theory for that P form, for P plus form gauged field.
And what is not properly defined? So like the non-invertible non-finite symmetries, all right?
No. These are also properly defined. There are non-finite symmetries which are non-invertible, but rather than continuous, so having like a continuous parameter transformation, they have a parameter transformation which is any fractional number. So in Q mod Z. So if you want, it's discrete, more or less, but it's non-finite. It's labeled by P mod n instead, any P mod n instead of a U1 parameter. That's what I'm saying. And there are
you mean the value, the eigenvalues of such operator?
Yeah.
I see. Thanks.
Yeah, I mean, if you want the coefficient, these two coefficients will create what is P over n, the coefficient on front of these two terms. This corresponds to the transformation parameter of the symmetry.
Yeah, thanks.
Sorry, can we obtain some symmetry TFT for some non-Lagrangian theory, such as the class S theory?
Yeah. So the question is whether there are any symmetry TFT for non-Lagrangian symmetry, for non-Lagrangian theories, if I understood right.
Can we also start from supergravity theory and using a compactification and then obtain?
Yeah. There are examples of in class S. This is a good way. I think there have been already a couple of papers discussing class S. But yes, you can use that's the advantage, right? You can use the string theory realization to, I think I have an example, sorry, I mean, I'm not being stupid, maybe. Okay, for example, this Giras Douglas n equals 2 theories,
Oh,
you
okay.
can see, you can construct the symmetry TFT from the geometric engineering type 2B. So now the space you're compactifying on is the link, which is a Sasaki-Einstein, with some torsional 2 cycles, and you can construct even the non-invertible. Sorry, this is a backup slide from a talk I given, but you can see you can construct also the non-invertible duality defects in this symmetry TFT. So this is very powerful, I would say. So you don't really need a Lagrangian for the theory to study the symmetry TFT. Of course, the symmetry TFT has a Lagrangian. In this case, does it? I think in this case, there's a Lagrange. The symmetry TFT. But that's not, the Lagrangian on the symmetry TFT doesn't depend whether the theory has a Lagrangian.
Excuse me?
Yeah.
Are there any symmetry TFT for maybe some finite non-abelian symmetry like S3 or?
Good.
Because you all discuss about abelian case, I suppose. And for abelian case, you can use BF theories, but
right.
I'm not
in
sure.
that case, you don't have a Lagrangian. That's the.
I don't have a Lagrangian.
Yeah, at least it's not known a Lagrangian, usually, I think.
But there are some theories for that.
There are some, there is some theory, some category theory for that. Yeah, I agree.
Nice.
And there is a symmetry TFT for that, just in terms, this symmetry TFT is given just in terms of topological.
Just you know the topological operators in that theories. And
such, and how they are related to each other, how they link, how they charge each other. Yeah, you know a lot of information. Yeah.
Can you also compute some partition functions for that symmetry TFT, or?
How do you compute the partition function?
Yeah, maybe without Lagrangians, maybe we can do some. I'm not sure. Yeah.
Yeah, maybe you can use some properties of the Hilbert space of TQFT. So if you know the Hilbert space of a TQFT, then I guess you can compute the partition function.
I see. Thank you. Yeah.
The Hilbert space must be finite, even if it's not abelian, right? So you can try to.
Okay, thank you.
You're welcome.
Hi, Fabio. May I ask a question? Can one also compute, for example, ground state degeneracies of the topological theories?
Ground state degeneracies. What? Well, this TQFT I'm not sure about that actually. Not 100% sure whether you can compute. Probably you can compute the ground state degenerate. It's just I don't know how you would implement such computation.
I see. Thank you. For example, for the non-abelian TQFT, for ground state, one can have a degeneracy. And for abelian case, it would be could be different. Yeah, sure. Thank you.
Yeah. But these are a TQFT computation that you can do on this symmetry TFT. I agree. I'm not sure. I'm thinking how this would be related to information about the boundary theory. That's probably I don't have an answer in mind, but I have to think about it.
I see. Thank you very much. Thank you very much. I can discuss with you later. Thank you. Thank you. Are there other questions? If there's no other question, let's thank Fabio so much again.
Thank you.
Thank you. Thank you so much, Fabio. I can just, yeah.